Okay, let's jump right into this explainer and trace the wild, mostly invisible life cycle of water. We're talking about that massive, continuous exchange between the atmosphere, the oceans, and the land that actually drives every single weather event we experience.
Here's our roadmap. We'll start with the invisible water around us, move on to evaporation and condensation, and check out dew, frost, and fog. Then we'll hit the 4 types of clouds, dive into precipitation, and wrap up with global rainfall patterns.
Section 1. The invisible water around us.
Now, it's pretty wild to think about, but the air around us holds up to 4% water vapor by volume. To measure that, meteorologists use 2 different terms. Absolute humidity is literally the sheer weight, the actual physical grams of water floating in a cubic meter of air. But relative humidity, that's entirely dependent on temperature, mainly because warm air holds a lot more water than cold air. It's essentially a percentage that tells us exactly how full the air's moisture tank is at any given moment.
So what happens when that tank gets completely 100% full? Well, when the air cools down to a specific temperature where it hits total capacity, we call that the dew point. At this exact temperature, the air is totally saturated. It is physically incapable of holding even one more drop of invisible moisture. And that means all that hidden water is about to make itself very known.
Section 2. Evaporation and condensation.
Making that invisible water visible is really just about subtracting heat. First, moist air cools down and loses heat. Second, as it cools, its capacity to hold water shrinks right down to that dew point we just talked about. And third, the excess vapor condenses. But here's the absolute coolest part. It needs something to grab onto. It actually condenses around microscopic floating particles, things like dust, smoke, or even tiny flecks of sea salt. Without all that floating debris, our weather simply wouldn't exist as we know it.
Section 3. Dew, frost, and fog.
Depending on the temperature, that freshly condensed moisture takes on some pretty familiar forms right in our own backyards. The ideal conditions, clear skies, calm air, and long cold nights, are exactly the same for both dew and frost. The only differentiator is temperature. If the dew point is above freezing, you wake up to wet shoes from the grass. That's dew. But if the dew point drops below freezing, the moisture bypasses the liquid stage entirely and deposits directly as tiny ice crystals. Presto, you've got frost to scrape off your windshield.
Now, what if that condensation happens on those floating dust particles right near the ground instead of on solid objects? You basically get a ground-level cloud. We call it fog when it's so dense that horizontal visibility drops to less than 1 kilometer. If you can see a bit further, between 1 and 2 kilometers, that's mist. The kicker is that mist actually packs more moisture per nucleus than fog does. Oh, and as a quick aside, if you mix industrial smoke into the fog, that's exactly how we get that dense, hazy condition known as smog.
Section 4. The 4 types of clouds. Looking way up into the free air, that exact same condensation process creates massive structures, and altitude totally dictates how they look. Way up high, between 8 and 12,000 meters, you've got cirrus clouds, feathery, detached, and made completely of ice crystals. Drop down a bit, and there are cumulus clouds, those classic fluffy cotton wool patches with the flat bases. Stratus clouds do exactly what they sound like. They form massive, layered sheets that blanket huge portions of the sky. And finally, nimbus clouds. Those are the dark, opaque, dense masses hanging lower to the ground that are just packed with rain.
Section 5. What comes down? Precipitation.
Eventually, continuous condensation makes all those tiny particles too heavy for the air to support, and gravity takes over. Sure, rain and snow are the most common, snow being those delicate hexagonal ice crystals forming in sub-zero temps. But things get fascinating with sleet and hail. Sleet happens when frozen raindrops fall through a freezing layer right near the ground. Hail is even wilder. Solid pieces of ice get bounced around, up and down through colder layers in a storm, building up concentric layers of ice over and over until they plummet to the earth.
So how does all this water drop across the landscape? Let's check out orographic or relief rain. Imagine saturated air being pushed up the windward side of a mountain. As it rises, it expands, cools, and unloads heavy rain. But by the time that air crests the peak and descends down the other side, the leeward side, it warms up and actually absorbs moisture. This creates a totally dry area known as a rain shadow. It's the literal reason why one side of a mountain can be a lush forest, while the opposite side is practically a desert. While mountains drive orographic rain, convectional rain is all about intense heat. The heated surface warms the air above it, which shoots straight up in convection currents, cooling rapidly to form towering cumulus clouds. This triggers those heavy, thundering, but generally brief downpours we see in equatorial regions or on hot summer afternoons. Then there's cyclonic rain, which is driven by massive extratropical cyclones and the intense collision of completely different air masses.
Section 6. Global Rainfall Patterns. 200 centimeters. That is a staggering amount of annual rainfall, and it consistently gets dumped on very specific areas, mainly the equatorial belt, monsoon coasts, and the windward slopes of coastal mountains in cool temperate zones. But freshwater definitely isn't distributed evenly across the globe. The general rule of thumb: rainfall decreases the further you travel from the equator out toward the poles. It also heavily favors coastal areas over deep continental interiors, which makes perfect sense since oceans supply the vapor. So while the equator gets soaked with over 200 centimeters, the central parts of tropical lands might only see 50 to 100, and the lowest amounts, under 50 centimeters, are reserved for those high latitudes near the poles or trapped in the dry mountain rain shadows we covered earlier. It really is a massive, never-ending atmospheric engine driven by heat and gravity. So take a second and look outside your window right now. Which part of this invisible moisture life cycle is happening right in front of you? The next time you wipe dew off your car or watch a dark cumulus cloud roll by, you won't just see the weather. You'll understand the exact machinery driving it. Thanks for hanging out with us for this explainer, and keep looking up.